Hi and welcome to my blockchain talk. This is mostly about a little project that has been keeping me busy lately, and I'd like to take you through it. Also, this is the recorded version of a presentation I will be giving soon, so it also serves as a practice round for me. So let's start with who I am. I'm Alex. I am the CTO of QSD, and QSD, we are a small consultancy firm mostly. We do consulting work for bigger clients. And we also partner with startups to provide technical knowledge to help them, well, basically to help them achieve their dreams. So, um, apart from I like tinkering with other stuff apart from software. Well, here you see a nice example of me at one of our QSD hackathons working on model airplanes, one of my big hobbies. And we got together in a little house for a weekend and we did some hacking, did some coding, and you see me trying out the balance of a plane we built together, which we actually flew, and it flew pretty well. So that was a really fun weekend. And I really like this idea of building tangible things as well. Also because it's very much an iterative process, kind of like building software. You have a design, you try it out, you see where it needs improvement. Sometimes you crash, but that's also a learning experience too. So today, you were probably thinking, what, really, blockchains again? I've been hearing nothing but blockchain lately, and you do have a point there, because I heard a very nice phrase lately which said blockchain is the new duct tape, and you do really see people trying to shoehorn blockchain into just about everything. There's a lot of stuff going on about it, a lot of presentations, but the main thing I noticed is a lot of them are either about the things you can do with blockchain, which is very useful because it does have a lot of very good uses outside of just cryptocurrencies, or they do try to go into some technical level, but until recently I didn't really get a grasp of how it really worked until I saw one presentation that went slightly deeper into the technical side of things, just enough to give me a feeling like, okay, I think I kind of get this, but now I really want to get it. And well, for me personally, the best way to actually really understand something is to build it. So I figured, why not? I'll start a toy project. And I figured I would do that with Akka. So this is what I did. I didn't completely start from scratch. I looked around online a bit and I found a very nice, very basic blockchain implementation called Naive Chain. It's written in JavaScript. It's very simple. It's only a few hundred lines of code, very much straight to the point. But it's not actually a functionally complete blockchain. What it doesn't do is proof of work. And I'll explain later why that is really important. So I wanted a little bit more than that. But I figured, you know what, I will just formulate some steps for myself. So I will start by taking Naive Chain and replicating it in Scala and Akka, because that's the other thing I really wanted to learn, Akka. Then when that is okay and I have something that works, I will take the next step where I actually add proof of work. And of course, the project needs a new name and I have a lame sense of humor. So from Naive Chain, we got the cynical chain. Once I have the fully working proof of work version, of course I'm going to build a cryptocurrency on top of it, because that leads me to the next step, an initial coin offering, and I will be filthy rich. Well, I'm still working on the coin. It's fairly finished by now, but it's not at the point where I want to publish or present it yet. And the first step, Naive Chain Scala, really isn't all that interesting. So I figured today I would focus on the cynical chain, because it has everything that is interesting about Naive Chain. But apart from that, it also has proof of work, which allows me to show actually what a blockchain in action is. But first, before we go into the whole blockchain stuff, something a little else. I am really dating myself by this reference, but because this, for the guys who were around in the 80s, this is a picture from Niels Holgersen, and the goose on the left is Akka, which is always what I have to think of when I hear the name. So I will try to do a quick explanation of the actors and Akka in under 2 minutes. So let's see if I can do it. Go. So what are actors? Actor-driven development is kind of like old school OO, but it's not quite. It's a paradigm kind of like OO, like functional, but slightly different. So what are actors? Actors are little entities of computation, and you cannot call methods on them. Actually, you cannot even directly talk to them at all. The only thing you can do is send them messages. And those messages, they end up in a mailbox, and the actor just processes those in order as they come in. Very simple. And the most important thing about it is it does that single-threadedly. So an actor doesn't actually occupy a thread. It gets handed a thread very shortly, but there will never be two threads working on an actor at the same time, which leads to the next thing. So actors can safely be stateful. You can actually have mutable state in an actor, and that's completely safe because you can be absolutely sure that that state will never be mutated by two threads at the same time. And finally, the messages you send, on the other hand, they absolutely have to be immutable. Because if you send mutable state in a message, another actor could theoretically modify it, and all the guarantees and all the safety that you get from this goes out the window. So this is a very powerful programming model for concurrent programming because it allows you to do very simple, safe operations in a concurrent environment. You might know Erlang, which is one of the better known implementations of the actor model. Akka does the same thing, except it is a library that does it in Scala. It's actually based on the original actor code in Scala, which was later spun out into a separate project. Yeah, I made it. So, blockchains. Let's look at a blockchain now. This is actually a visualization of a little tool I wrote myself. We will see that more on later on. So what is a blockchain? A blockchain is basically a distributed database with eventual consistency, and it is implemented as, well, basically as a linked list. So you have the top of the blockchain, which has a pointer to the block before it, which has a pointer to the block before it, and so on and so on and so on. And conceptually, what a blockchain allows you to do is it allows different parties online that do not trust each other to reach consensus over a series of events, actually. And events can be very loosely defined here, because in this case it's just messages that are being recorded, but they are recorded at a certain time. Now, if we look at the structure of a blockchain, we start on the left. On the left you have something called the Genesis block. And the Genesis block is something every blockchain has. It is one fixed block that the whole chain is built upon, and it basically serves as the root of trust. If you want to agree on a blockchain, you have to agree on a Genesis block. Everything else can basically be checked against that, but you have to agree on a Genesis block. Then if you look at the next block, you see it has a few fields. It has an index 1 because the Genesis block is 0. Then found by node 2. That is something that's particular to my implementation. We'll get to that. The nonce, which is part of the proof of work. Get to that too. Now it's getting interesting. We have the previous hash and the hash of the block. Now, the hash of the block is a hash code calculated over all the fields in this block. So you take all the fields in the block, you add them up, you calculate the hash over that. Means, of course, that if any field changes, the hash would change. Now we also have the other field here, the previous hash, which is in fact the hash of the block before it. You can actually see it if you look at this picture. The block on the right, it has hash dbed34c. Its previous hash is 580464d, which corresponds to the hash of the block before that, which in turn has its own previous hash 2b33684, which is the hash of the Genesis block. Now, this is an important thing because that previous hash field is actually also included in the hash of the block. And that means that the moment somebody were to tamper with one of these blocks, its hash would change. But that means actually that the previous hash of the next block would also have to change, and so on and so on and so on. So you can actually check any block against blocks that come before it. And this gives you a level of tamper-proofness, essentially. Now, basically, what does this mean? This means if you change a block in the blockchain, if you want to tamper with it and still have a valid blockchain, you have to recalculate all the blocks after that. Now, you might be wondering, okay, well, sure, but why does that actually, what does that give to me? Well, why is that even so important? Well, that's what we get to the next part, proof of work, because we actually make it artificially hard to add a block to the chain. So you've seen the hash of the block. The best way I have heard proof of work explained actually was to say like, okay, you put certain restrictions on the hash. So the hash is not any hash is valid. You put restrictions on it, and a simple restriction is to say like, well, my hash has to start with at least 4 zeros. Now, if you take one step back, you can basically say, so the hash for any given block has to be below a certain value to be valid. Well, and as you probably know, hashes are completely random. So you can't really know if the hash of a block will be below that number or not. But of course, now if I go back a second, the hash, if I want to have a hash in the block that actually satisfies certain conditions, and the hash is calculated over all the fields, I need at least one field that I can freely manipulate to make sure that I change the hash so that I can keep trying. Well, that's what the nonce is for. The nonce is, well, it's a short for nonsense. It's not a value that actually means anything. It's just a number, and we just increment it just to change the hash of the block. So basically what you do if you try to find a valid block is you change the nonce, calculate the hash, check if it's below a certain value. If not, you just move on to the next, you increment it again, all up until the point where you find a nonce that actually satisfies the difficulty function. Now, let's take a look at that a little bit more up close. So, here we have the basic blockchain class. It's you have here first the block message, which is basically just a message you can add to a block. In my case, messages are pretty much always strings, and they have a unique ID. And the unique ID becomes important when you start mining, because that gives you a good way to see if a specific message is already in the chain or not. I mean, I could add the message hello world to the chain 3 times, for example, but each of those would in fact be separate messages. And when we mine them, we want to be able to distinguish between them. So then we get to the genesis block. The genesis block is basically, like I said, it's a fixed point. So it's also an object in this implementation, as you can see. And well, it's not all that interesting. It has a very simple message called genesis block in there with UID. Actually does have a valid hash, even though nobody will ever validate the genesis block, since it is basically our source of truth. Then we have the case class block, which is essentially just a straight up representation of what you saw in the picture. So it has the index, the previous hash, timestamp, who found it, stuff like that, sequence of block messages, the nonce, and the hash. And the hash here is represented as a big integer, so it's easy for us to compare them. Well, the blockchain object doesn't do all that much interesting stuff either. As you can see here, we define the hash function and the difficulty function. And those were in the slide as well, but I kind of skipped over them. Are basically just type aliases for a function that takes a block and gives you a big int, so that you can actually compare the two things. And we have 2 default implementations of them. The difficulty, the hash function, is very simple. It basically just takes the string, all the fields, makes a string, gives you an SH265, 256, sorry, hash of that one, very straightforward. And the difficulty function actually comes from another project called Naive Chain, And what it does is it is just a slowly sliding scale. So the first three blocks, sorry, are actually really simple to get, and then they slowly get more difficult every 3 blocks. This is a very simple version, of course. Things like Bitcoin use a much more complicated algorithm, which is actually based on how many people are mining. Here we just base it on the chain length. And then there are 2 other difficulty functions mostly used in testing. There's no difficulty, which basically gives you the max number, so any number will be below that, and impossible difficulty, which is 0. Well, you cannot have a negative hash, so no hash will be below 0. And those are mostly useful for testing. Then we get the actual blockchain class. Now, if you look at the blockchain class, I actually implemented it also as a linked list, as a very classic linked list, in fact, with a head, which is a block, and a tail, which is again a blockchain. Except, of course, you have the special case of the Genesis block, which has no tail, so I implemented it as an option of a blockchain. And that allows us to do some interesting things. Well, here is actually, for example, if I want to list all the blocks, basically, what I wanted to write was this, where I can basically just say like, well, that's the latest block, and then I recursively append the blocks of the other chains. It's very nice, very clean. It's guaranteed to give you a Stack Overflow on a large blockchain. So I went for a slightly more verbose implementation, which is actually tail recursive, so that even if my blockchain is 50,000 blocks, this will still work. And basically what it does is it says blocks 0 and blocks with an empty list, and then just passes the prefix down. It's a simple recursive implementation. I did learn a few nice interesting things here actually. For one, the tail recursive annotation isn't actually needed in Scala to make something tail recursive, but it's very wise to put it on, because the Scala compiler can be pretty finicky about what it does and does not actually consider tail recursive. For example, a method has to be private to be tail recursive. That's it. Makes complete sense. I didn't know it until now. So then we have the first block, which is basically, this will always be the Genesis block, but we still walk the chain to calculate it. This is mostly just used for validation. Contains is a similar thing, where we recursively go down the chain to see like if it has a specific message. Then we got a bunch of utility methods, which are mostly used just to easily add messages to the chain. So it will basically say like, okay, I will generate a block with this message in it. Generate block itself, pretty straightforward again. It just generates new blocks. And then we can append blocks to the chain. We can actually replace all the blocks from the chain, which leads to us to creating a new chain and just step by step appending each of the blocks, seeing if we still get a valid chain from that one. So this is actually a nice one where you we do a fold left, starting with a current chain, and then one by one append the chains, and each of those could actually give us a try result, because it can fail. Because if the block that we are adding is not valid, we will get a failure result. So we basically flat map that with the add block. And if all the blocks are valid, then in the end this will return a blockchain which is valid. Then we have the add block method, the valid block method, and actually now we get to the more interesting part, like when is a block actually valid? Well, there's a whole list of things that a block has to satisfy to be valid. If, and maybe I should say a bit more quickly. So if we actually get a question like, okay, hey, I have a new block here. Is this a valid block to add to this chain? That's what this method says. Well, it is a valid block to add to this chain if we validate it against our current latest block and it is valid. And we do that by checking, well, okay, the index should be 1 more than the one of our current valid block. The hash should point to our current latest block, because it's a chain, as we saw. The timestamp, well, it should not have been generated before our latest block, then it's definitely not valid. The other one, it also shouldn't be generated too far into the future, because, so let's say I generate a block and I give it a timestamp of the year 3000. That would mean that until the year 3000, no new blocks are accepted anymore. So we don't want that. But we do want to account at least a little bit for clock skew between the nodes. So we compromise a bit and we say like, well, if it's no more than 5 minutes into the future, we'll accept it. We double check the hash because you get this block. You do not actually trust that it is a valid block. Somebody could have tampered with it. So we check the hash that is in the block and compare it to what we get if we've hashed the block. Well, block has to the hash has to be smaller than the difficulty function for this block. So whatever we require for the difficulty to be, it has to be smaller. And one more, none of the messages in this block should already be in the blockchain. Apart from that, basically, if you want to validate a full blockchain, which we usually would try to not to do, but if you want to do it, you basically say like, well, if the tail is nothing, then the head should be the genesis block, else our current head should be, that one should actually be valid against the head of our tail, and the tail itself should also be valid. Very simple. And finally, this is also a nice one. I had to actually overwrite the toString because it is a recursive data structure, and that means that the toString also does recursive calls, which again gives you a Stack Overflow if you have a very nice long chain. And we want to be able to have long chains. So, so this shows the verification again, but I already went through that in my IDE. So it is basically just a whole list of conditions that a block has to satisfy in order to be valid. Now, as I said before, a blockchain is not just a data structure, it's actually a distributed database. So what we just saw was just the blockchain, the pure blockchain data structure, which is basically just a linked list. So in itself, it doesn't really do all that much yet. You really start to see the power when you see it in a distributed context. Well, we have a little Bioshock reference here, no gods or kings, only man. And that here means actually there is no central authority in blockchain. But as you remember probably, that blockchain was created to be the underlying mechanism for Bitcoin, which is about money. So you really do want to be able to trust that nobody messed with your transactions, that especially if somebody gave you some money because you sold them a product or you did some work for them. You do not want that transaction to mysteriously disappear from the ledger, leaving you out of money. So how do you trust about that? Because how do you actually get all these different parties on the internet, all of whom could be running a hacked client that tries to cheat? How do you get them to trust each other? Well, that is basically the core of how the peer-to-peer networking from Bitcoin, from blockchain works. Now, first, I'll start a little bit about how we set up the peer-to-peer network itself and what how my application itself looks. And that's like this. Each of those little circles you see here is a Akka actor. So you have the REST interface is not an actor, it is just an interface that talks to them. You have the peer-to-peer actor, which is basically the central point in the dispatcher in this application, because it can talk to other peer-to-peer actors of other nodes. So if another computer is also running the same application, its peer-to-peer actor will talk to that other application node's peer-to-peer actor, and they do that through something called Akka actor remoting. And inside the application, we also have a few more actors. We have one actor, which is basically the guardian of the blockchain. It's called the blockchain actor, and what it does is that actor actually holds the blockchain for the application and makes sure that all the modifications to that blockchain take place in a properly structured way. And that really takes advantage of the fact that actors only allow single-threaded modification to fields. So there's always only one truth in the application. Then we have the mining actor, whose job it is to actually find a valid block for a given set of messages. So if I request to add some new messages to the blockchain, the mining actor is actually responsible for finding a valid block, except it doesn't do that itself, because while it is looking for that, it could actually get a new request for more messages. So what it actually does is, for each unique set of messages it has, it spins up a mining worker, which is a new actor, which only has a task to actually do the work to find a block containing that specific set of messages. Now, the strategy I chose here is actually pretty a pretty greedy strategy. Let's use that word. As in, if message A comes in, we'll spin up a worker just to look for message A. If in the meantime a message B comes in, we'll spin up a second worker to look for both A and B. And then those two workers are basically racing each other. So whoever actually finds a new block first, a valid block first, wins. And then depending on which one it was, we will see how we proceed from that point. I'll show that in the coding later on. And basically those are the things. And you can also see the messages here that are exchanged between the actors, but I'll go to those in more detail. So, first of all, of course, before you can talk to your peers, you have to find your peers. Now, I used a very classic mechanism here, and actually also a very naive mechanism, where basically there is one fixed point that everybody knows, and that is the seed node. And everybody connects to the seed node first, and then the seed node will tell them who else is on the network. So if we those are the messages we can exchange, but we'll get to those when I go through the code. So basically you start by connecting to the seed node, and you send a message to the seed node. That's what always happens. Now, as I said, the peer-to-peer actor also serves as a dispatcher. So it will receive some messages for that it actually cannot handle itself, especially in this case a whole bunch of the messages meant for the blockchain actor. I'll show you the blockchain actor in a minute. But it uses a very nice Akka feature called forward. And what forward does is it sends the message on, but it preserves the sender address from the original requester. So if that other actor answers, it will answer directly to whoever asked the question without the dispatcher having to get in the middle again of that one. If the blockchain is updated, we tell the mining actor, because that probably should stop mining. If we get a request to add new messages to the blockchain, we use something in Akka called an ask, where it says like, okay, please give me the blockchain. So we send in a message, and we save the context wherein we actually got the message, in which we sent the message. And if a reply comes in within a specific time, we can just pipe that to the mining actor. So we do a little transformation on it, we create a new request, and then pipe it to the mining actor. This is a very powerful mechanism in Akka. You shouldn't use it too much, because you do in fact create a temporary listener. But for things like this, where you have to actually aggregate and transform a request, it is very nice and powerful. We can also get a mining result back from the mining worker that we saw in the picture before. But at that point, we don't actually do anything yet, because the world may in fact have changed or whatever. Like I said, this is all the actors do in fact run concurrent. So just the fact that the actor found a block on a specific blockchain doesn't actually mean the block is valid, because in the meantime our blockchain could already have changed. So what we do is we just send it to the blockchain actor, let that actor decide what happens. If that actor actually accepts the block, then we will get this one a blockchain updated, which actually means the block was valid, it was accepted, we now have a new blockchain, and then we will stop all the mining actors. If you look at this mechanism, you can also see, like, so it's very well possible that in the time between us receiving this blockchain updated event and us actually stopping the miner, one of those mine result blocks could still come in. So that's why we do this like this. Then we have the broadcast request, which just basically says like, hey, please send this to all your peers. And then all the stuff to actually get the peers. Now this is a very, very naive peer-to-peer network, as in every peer in the network knows every other peer in the network. So it is chatty as hell, but for this simple thing, it is actually one of the better ways to handle it. And in fact, if we get a new peer, we do go through this sequence of steps. We put a watch on it, so that means that actually we request notification the moment that it dies. We send it a handshake with our name, and that actually also gives it our address. We ask it for its peers, so it will then send us a list with all the peers it knows. This one is actually particularly useful, of course, when you first connect to the seed node, because then you will get a list of all the nodes in the network. And we'll actually also broadcast the fact that we just got to know a new peer. So this does mean that you actually get a lot of messages for peers you already know, which of course is why we check here that we don't already have this peer. And finally, we also ask it for its version of the blockchain. Well, then and the rest of the stuff is mostly just handling a request. So if we get asked for our peers, we send it. If we get a handshake for somebody else, we just add it to our list of known peers. But we don't actually do anything because that person already knows us. And we do not broadcast this person because we trust that the person that shook our hand actually broadcasts us. And probably probably will introduce itself. Well, we can actually peers, and if this is also an interesting one, terminated is a Akka system message which you get the moment that one of the actors actually dies that you know. Okay, so we'll very quickly go to the blockchain actor. Blockchain actor, let's look at the messages first. Well, we can query the latest block, ask for a new block, query for everything. It's all very straightforward. So let's take a look at what actually happens when messages come in. So we can get a query for the latest block, a query for the whole blockchain, and we just reply with whatever we have. That's not so interesting. We can have also, well, this is one small difference. We can actually get a query for the full blockchain, which includes the difficulty function and the hash function. So that's something that we will only send internally because you don't want to serialize that. These we will actually serialize over the network, and we only send the blocks, which is pure data. Then we have this one, the two methods that are actually interesting. So what will we do when we get a new block? So say one of our peers says, hey, I found a new block. What happens then? Well, basically, we do a very simple check to see if it actually refers to our latest hash. I mean, if it doesn't, then it's not a valid block. But if it does, we try to add it to our blockchain, and that either gives us a success, in which case we switch our blockchain field. Like I said, actors can actually be stateful, so we can just safely switch the field, and we broadcast the fact that we have a new block, and we just send a new block, and we send internally a message to say like, hey, our internal blockchain has been updated. Well, and if it fails, then we just log the fact that we refuse to add this block. But now the other one. So we do get a block, but its hash doesn't match. Well, there's a few things that, it could be an invalid block, but it's also very possible that it is in fact a block that is just further ahead of the future. So we are lagging 2 or 3 blocks behind. So to make sure we handle that scenario, we just ask all our peers like, hey, please give me your whole blockchain at this point. So give me all the blocks, which then would come in this method. Now, if it's an empty block list, we don't do anything. It's not interesting. If the index of that block is, well, basically if that blockchain is not longer than our current chain, we also ignore it, and we do that by a simple check on the index. because if the indexes were not representative of the length, the blockchain wouldn't be valid anyway. Or if it is actually longer, then we try to build a new blockchain with those blocks, and we actually say blockchain.with blocks, which replaces the blockchain, but it does keep the difficulty function and the hash function. So it is basically, it says like, hey, use these blocks and build a whole new chain starting at the genesis block. And if that succeeds, which means that all the blocks are valid, then we do the same thing as we saw before. We actually say like, hey, our newest latest block is this, and we send an internal message to say that the blockchain has been updated. Now, the last one is mining, which is actually in two parts. So we have the mining class itself, and we have the mining worker. Well, the create worker method creates a new worker. It doesn't really do all that much. Okay, so what can happen here? Well, if our blockchain changes, we send all our workers a poison pill, because all those workers will be trying to create a new block, find a new block based on what was our latest block. Since that slot has now been filled, none of those blocks would ever be valid, so we just kill the workers. We're very rude, we send them a poison pill, and they subsequently all die. Then we check the messages we are looking for, because we have a set of messages up there that we keep, and we filter out all the messages that are now in the blockchain. And then we see like, okay, is there still anything left to mine? Are there still messages that I was trying to put in the block that haven't been put in the blockchain yet? If so, I create a new mining request to mine those messages. The second one is actually where we normally start. If we get a request to mine a block, we filter first those messages to make sure that none of them are in the blockchain, because we can in fact get an outdated request, and we don't want to waste our time trying to mine a block that will never be valid because it has a duplicate message in it. If after that filter we do still have messages, we add them to our set of messages that we're looking for. We actually ask all our peers also to start mining, so we don't keep this information to ourselves. We're saying like, hey, we are now going to start mining this set of messages. Everybody else, please do the same. This adds the chance that that block actually get mined. And then finally, we spin up a mining worker, and we watch it so that we can also check if it dies properly, and we ask it to mine a block with those messages. And finally here, when we get a terminated message from a worker that has just passed away, either because we sent it a poison pill or just because it finished working, found the block, and then committed suicide essentially, we remove it from our set. And there is a little bit of a special case here where all our miners quit. So we no longer have workers just running, but we do still have messages to run. In that case, we spin up one new worker and ask it to mine everything that we are now looking for. Now, if you then look at the mining worker itself, you might expect it to have one big busy for loop where it tries nonces in a long list. And you could in fact do that because it is a dedicated worker. It's not as easy to stop it though, because if the worker is that busy, it will block a thread and it will actually not check its mailbox. And we want to be able to interrupt these workers. So we use a slightly different mechanism. What we actually do is we get a message to mine a block and the message, that's actually worth showing, has two default things. So if you create a mine block request, it will by default set the start nonce at 0 and the timestamp at whatever the time is. But if we get a request to mine that, and we do some logging if it's 0, we try to create a new block, check if it actually if it's satisfies the difficulty function. I mean, we could actually just, if you want to do it naively, you could create a new block, add it to the blockchain, and then the whole block gets validated. And we don't want that because we, of course, want to beat all the other miners. So we want to be very quick and cheap. So we do the least calculation that gives us the biggest chance. So we validate once if the block is actually would be able to be valid. And after that, we just only try to find the difficulty. And if we find it, we report back to the peer-to-peer actor, and then we stop ourselves. And we do a little bit of logging after we win. Now, I am completely running out of time here, so I will go through a few next slides very quickly. So these were the messages for the blockchain. Mining, we also saw that. The nuts and bolts. Okay. To effectively show you a peer-to-peer, we will see that in a minute, I'm using Docker Compose. And Docker Compose allows me to basically spin up the same application 4 times in an container and set up a little network. Well, actors talk to each other through actor remoting, which is a very nice, simple way to actually send messages to each other over a network. And the HTTP interface is actually done by Akka HTTP, which just allows a very basic, simple control interface. Now, the web interface has a few endpoints, and what you will be seeing me do is just talking through it with curl. So, now comes the big part. So far, we have been talking a lot about how you can actually have distributed trust. Well, how can you, in fact, do that? And how do the things that we have seen so far allow that? Let me spin up my little system here. I have 4 nodes now, and those 4 nodes, they simulate 4 computers running over the internet. And you can see them here in my little visualization. Well, right now, the whole chain is empty. You can just see the Genesis block. And I will now send one of these nodes, node 1 in fact, a request to add some data to the block. You see I get a response back with, and now we see something interesting. We see a couple of blocks with different colors. The colors are in fact determined by which node found the block. Now what you see happening here is that the top 2 nodes, node 1 and 2, have an orange block, so that was actually found by node 2, and the other 2 were actually found by node 3. Now this is somewhat random. What happens here is the moment a node gets a request to mine, it spins up its own miner to find a block that is valid. But since the blocks they are trying to find are not completely identical, mostly caused by the fact that they each put their own node name in it, they don't actually find a valid hash at the same time. And that in turn means that there is a chance that they actually receive a valid block from one of their neighbors before before they found it themselves. And in this case, you see it exactly 50-50. 2 of the nodes actually found a block themselves and accepted their own block before getting one from the neighbors, and 2 actually accepted one of the neighbors' blocks. Now, I will add some more data. Now you see actually that one of the nodes moved to the other chain. That means that it got a new block from its neighbor, actually again before it found the old one, but it was basically it then switches to the chain of the where it got the block from. So you now see that node 1, 3 and 4 are all on the chain started by the block found by node 3. Now if I add some data again, you can actually see that we get a little bit more divergence again. But so we still have node 2 on its own completely own timeline. And nodes 1 and 4 have the same view of the world, and node 3 has a slightly different view. So we get a little bit of divergence at this moment. And we get even slightly, we get a little bit more divergence yet. And all of a sudden, boom, now we are in sync. Now this is interesting, what happened? If you look at the nonces, you actually see that the first ones are all 0. Then the second one is 33, 14, 13, 173. So the nonces are slowly rising. There is some variance in there, but they do rise. That means it takes longer to find a block. And if it takes longer to find a block, the chances get bigger that there is one node that finds it early enough that all the others pick it up. So it gets the chances good. Now if I add one more, it kind of depends. This is nice. I was hoping for this one. We can get some divergence again, because now they did find it, some of the nodes found the block quicker again than the other ones. But you also see that up until the point where we were, so all the orange blocks, that doesn't change. And that will never change, because they are all in agreement on that one. And this is actually shows very nicely how the two mechanisms together, proof of work plus longest chain wins, which is basically just how a consensus is reached, slowly moves you towards a situation where you can pretty much always agree upon what has happened in the medium past. So what has happened very recently, that's usually still a little bit in disagreement, which is why people always say, like, if you do a transaction in blockchain, wait at least like 4 blocks for it to be completely final. Well, that's exactly what you're seeing here now. If your transaction is in index 2, it'll never change. If it is in block 6, on index 6, well, if you're on the red chain, you might get lost. Actually, you might get lost if you're on the green chain as well. Because, well, here we see that it's still diverging. Yeah, you can see the red chain won, in fact. So you can see that this is how consensus is reached. But funny is, all those nodes, none of them trust each other, but they do all trust by the same, play by the same rules, and that actually helps consensus be reached. So all the source code of the things I have shown just now are on my GitHub. I would really welcome any pull requests and stuff like that, any feedback, any improvements that can be made, so please let me know. Well, obviously we won't have questions, this is a video. And of course, finally, we at QSD are hiring. If this is the kind of stuff that gets you excited, if you like this, if you want to talk with us, hang out with us, drink beer with us, please come find us sometime, and I'll be happy to talk to you.